Hi, I'm Songbin from Postec South Korea. I'm excited to present our work, LaughTalk, Expressive 3D talking head generation with laughter. This is joint work with Hyun, Tae, Suekyeong, Janghoon, and Professor Oh. Let's first have a quick preview. In this work, we propose a new task, speech-driven 3D talking head generation with laughter. For this task, we curate 3D talking head dataset, which we call it LaughTalk dataset, containing pairs of audio, 2D video, and 3D face sequences. Using this dataset, we train a 3D talking head model, LaughTalk, which can simultaneously talk and laugh. Speech-driven 3D talking head generation is a task of animating 3D talking head with the input speech. The correlation between speech and facial movements enables the driving of 3D facial animation with the input speech signal. 3D talking head offers promising applications in various fields, such as film production, computer gaming, or providing immersive interactions between humans and computers in virtual realities. Existing methods of 3D talking heads have shown accurate lip movements in sync with the input speech. However, these methods have several limitations. Firstly, when the input speech contains non-verbal signal, such as laughter, these methods fail to express such signal. Secondly, since existing methods use vertices for the output representation, they fail to change the shapes of the 3D talking head, but only allows to generate within a fixed number of face templates. The reason for these limitations is because there's no dataset to tackle these challenges, and without such datasets, no models have been able to address these limitations. Therefore, in this work, we propose a dataset that includes both verbal and nonverbal signals along with the 3D parameters. And trained on this dataset, we propose a model capable of addressing these limitations. More specifically, our proposed model generates a 3D talking head that can simultaneously express both verbal and nonverbal signal, especially laughter. As demonstrated, the 3D talking head successfully laughs in sync with the laughter in the input speech. Furthermore, our model utilizes the 3D output representation, allowing for the manipulation of the shape and identity of the 3D talking head. And why we keep focusing on the nonverbal signal, especially laughter? Humans interact with each other using both verbal and nonverbal signals. Among nonverbal signals, laughter is a distinct one that conveys social and emotional nuances. Moreover, laughter plays a vital role in human-computer interaction by providing immersive experiences and establishing intimacy. This motivates us to teach the 3D talking head to express laughter signals along with the verbal signals. We begin by collecting 3D talking head dataset. From a 2D video dataset, we filter out noisy videos, such as videos without faces, abrupt head pose changes, or videos with non-active speakers. And we only collect the videos with laughing and talking faces. Then, using existing 3D face reconstruction methods, we reconstruct 3D face from these collected 2D videos. This results in collecting the pairs of 2D video, corresponding audio, and 3D flame parameters as shown in this example. We collect two different subsets. The first is LaughTalk Celeb, containing samples of laughing and talking videos, while the second is LaughTalk Mid, which contains neutral talking samples. Here are more examples of our dataset. Using this dataset, we propose a two-stage training model, LaughTalk, to synthesize 3D talking head that can talk and laugh. In stage 1, the model learns to animate the 3D faces with speech-related signals. The input speech is fed into the stage 1 model and outputs sequences of the F heads. These F heads are built with the flame parameters, including expression and jaw pose parameters. Therefore, by feeding these F heads to the flame model, we can generate animated 3D talking heads. To ensure the stage 1 model to focus on the verbal aspects of speech, we train it on LaughTalk Meet dataset, which contains only neutral talking, and the expression and 3D landmark losses are used for training. After training the stage 1 model, we proceed to train the stage 2 model to animate 3D faces with both speech and laughter. Here, the pre-trained and frozen stage 1 model is embedded in the stage 2 model. Since stage 1 model was trained to express verbal signals, the rest of the stage 2 model focuses on synthesizing the residual part of the audio, which is the nonverbal signal. Therefore, by merging the outputs of the stage 1 and the residual part with element-wise addition and fitting them to the flame model, we can generate 3D talking head that simultaneously expresses both verbal and nonverbal signals. We trained the stage 2 model with the LaughTalk celeb dataset, which contains talking and laughing samples, and the reconstruction losses used for training. These are the visualizations of each model's output. As shown, stage 1 model outputs lip movements in sync with the verbal aspects of the input speech. By combining with the residual outputs, the final outputs of the stage 2 model are capable of expressing both verbal and nonverbal signals. Here we present some qualitative results comparing existing models with our proposed LaughTalk model. We test on the existing models with their official checkpoints.
Around a little, and Howard, old vet, he's like, cool. It's just like, I'm gonna roll with this.
As shown, only our model can express both talking and laughing in sync with the input audio, while the others fail to do so. For a fair comparison, we also compare with the models, which are trained on the LaughTalk dataset.
Like, waiting on what I'm gonna do right next, so that's the question.
Today we had just trying to do something to keep me occupied too. I'm going stir crazy.
Despite this training, the existing methods without two-stage training fail to accurately express both verbal and nonverbal signals. Our model doesn't always laugh in response to every speech. When given a speech with a neutral tone, the 3D talking head talks normally.
Land-based radar would help with this task.
However, when the audio includes both laughing and talking, the model successfully conveys both signals.
Muy tranquilas, pero es uno de mis lugares favoritos. Pues estos son mis 5 lugares favoritos.
Since our model leverages flame parameters for output representation, this offers some interesting user controllability. Firstly, our model allows users to manipulate the shapes and identities of the 3D talking head, even with the same input speech. Furthermore, the output representation of the LaughTalk model can be directly used for rigging the neural avatars with photorealistic and high-quality textures. This may open up practical and interesting applications for the users. In conclusion, this work goes beyond the capabilities of existing 3D talking heads by effectively expressing both verbal and nonverbal signals. And to achieve this, we propose a new dataset and a strong baseline model designed for the expressive 3D talking heads. We believe our work demonstrates significant potentials for scalability. Given that design choice of our approach is independent to specific nonverbal signal, it could be extended to express diverse types of nonverbal signals, such as surprising and crying. Furthermore, expanding the capabilities of 3D heads to include understanding and reacting, in addition to talking, might be an interesting future direction to explore. That's all for the presentation, and for more details, please visit our project page. Thank you for listening.